Hey everyone, and welcome to this one-shot series on continuity and differentiability. In this session, we will talk specifically about continuity only. So, let us begin. So, what exactly is continuity? Let us try to understand the definition of continuity first. So, a function is said to be continuous if there is no break or jump in its graph. So, if you have a graph and if that graph is very smooth and if there is no jump or break in that particular graph, then we say that the function is continuous. So, that is the definition of continuity. Let us see an example. Here we have a graph. Here we have the x and the y axis. So, we have a function y is equal to fx, and suppose we have a graph. Now, observe this graph very carefully. Now, can I say this graph is not a smooth graph and it breaks at this point, right? So, if you see over here at x is equal to a, the graph is breaking. And since the graph is breaking, we can say that this particular graph is discontinuous, that is the function is discontinuous at x is equal to a, correct? Discontinuous or not continuous, non-continuous, same thing. But if you have a look at the other graph, see over there, now this is a smooth graph, right? From this point to this point, correct? There is no break. So, can I say that this function y is equal to fx is continuous? And even if I want to check the continuity at point A, so you can see that at point A, there is no break here. So, since there is no break, we can say that the function is continuous. I hope this part is clear to all of you. Okay, let's continue. So, this graph has no break, and therefore we can say that it is continuous at x is equal to a. Now, let us see an example. Check the continuity of given graph. Now, we are supposed to check the continuity of the graph. This is very simple. Graph is given. We are supposed to check whether the graph is continuous at x is equal to -3, -2, -1 and so on. Fine. So, wherever you see breaks, there the graph is discontinuous. Wherever you see there is no break, the graph is continuous. So, if I look at -3, here there is no break. If I look at -2, here there is break. If I look at -1, the graph is smooth, there is no break. At 0 also there is no break. At 1, there is no break. At 2, there is no break. At 3, there is a break. So, we can say that at x is equal to -3, the graph is continuous, or you can say the function is continuous. That's a better way of saying it. At x is equal to -2, the function is discontinuous or not continuous. At -1, it is continuous again. At 0, it is continuous. At 1, it is continuous. Also at 2, it is continuous. But at 3, if you see, 3 it is breaking. So, it is discontinuous. Fine. I hope this part is clear to all of you. Okay. Now, let us see an example. Check the continuity of the function fx, where the function fx is 1. So, fx is what? It is 1 when x is less than equal to 0, and fx is 2 when x is greater than 0. Correct? So, fx is equal to 1. That is nothing but y is equal to 1, isn't it? So, how does the line y is equal to 1 look like? It is a line parallel to the x-axis. If I also talk about y is equal to 2, y is equal to 2 is a line parallel to the x-axis again. So, when x is less than equal to 0, the value of the function is 1. This is as good as y is equal to 1. And when x is greater than 0, the value of the function is 2. Correct? So, when x is greater than 0, that is on the right side, the value of the function is 2. So, this is your 2. And when x is less than equal to 0, the value of the function is 1. Let us take it as -1, that's better. So, this is like your -1 here. I'm just changing this as -1. Doesn't matter, even if you take 1, then also it will look something like this. Same thing. So, yes, anyways, there is a break here, isn't it? This is breaking. This graph is breaking, isn't it? So, we can say that we cannot draw this graph without lifting the pen, of course, because there is a break. It's a break at 0, not 2. Because at 0, what's happening is this is getting separated. Okay, let's continue. So, mathematically, a function fx is continuous at point A. So, when do we say the function is continuous? We say the function is continuous at point A if limit x tends to a fx is equal to f of a. If this condition is satisfied, then we say that the function is continuous. If this condition is not satisfied, the function is not continuous. Simple as that. Okay. So, let us see an example. Check the continuity of the function fx is equal to x plus 3 by x minus 3 at x is equal to 2 and 3. So, we are supposed to check the continuity of this particular function. Obviously, this is a rational function, isn't it? We're supposed to check the continuity of the rational function at 2 points, at 2 and then at 3. So what are we going to do? Let's see. We're already given with the function fx is equal to x plus 2 by x minus 3. So at x is equal to 2, we'll put x as 2 over here. So wherever there is x, you put 2, right? And then limit extends to a fx. Find out this. So limit extends to a fx will be limit extends to 2 x plus 2 by x minus 3. So we will put x as 2. We'll get 2 plus 2 by 2 minus 3. 2 plus 2 is how much? 2 plus 2 is 4 and 2 minus 3 is minus 1. So 4 by minus 1 is minus 4. Correct? And what is f of a? That is f of 2. So f of 2 will be directly put 2 here instead of x. So f of 2 is going to be 2 plus 2 by 2 minus 3. You're going to get the same answer, right? That is going to be f of 2 is equal to minus 4. Now f of 2 is minus 4. Limit extends to 2. Fx is also minus 4. This condition is satisfied. That means the function is continuous at x is equal to 2. But what about x is equal to 3? Is the function continuous at x is equal to 3? We need to check that, right? So how are we going to check it? Same thing again, at x is equal to 3, limit extends to fx will be limit extends to 3, x plus 2 by x minus 3. Now we will put x as 3. But as soon as you put x as 3, what will happen? In the denominator, 3 minus 3 is how much? 3 minus 3 is 0. So we are getting 5 by 0. So definitely this is not defined. We get infinity, right? So we can say that limit extends to fx does not exist. Basically, it is not defined. This does not exist. Why? Because this particular denominator is becoming 0. And since the denominator is becoming 0, we are not getting the value of the function at x is equal to 3. We should get some real value, correct? We should get some real value. If we get the real value, then only we can say that the function is continuous. If we are not getting a real value, if we are getting something like this, definitely the function is discontinuous. And always remember, whenever you have a rational function, and in that, if the denominator is 0, then that is discontinuous. If the denominator is not 0, it is continuous. Okay, let's continue. So fx is not continuous at x is equal to 3. Now let us see the concept of continuity at a point. So function fx is said to be continuous at a point x is equal to a. So function is said to be continuous at a particular point x is equal to a if the following conditions are satisfied. So basically these three conditions are very important. Let us try to understand. F of a should be defined. That is, the value of the function at that particular point should be defined. First thing. Second, the left hand limit, the right hand limit should be equal, and also the left hand limit and the right hand limit should exist. That should be equal to your f of a. We'll put a here, right? So limit x tends to a minus fx will be equal to f of a, and limit x tends to a plus fx will be equal to f of a. So indirectly you can say that this condition is very important. So if this condition is satisfied, the function is continuous. If this condition is not satisfied, the function is discontinuous. I hope this part is clear to all of you. And if any of these conditions is failed, then the function is discontinuous, of course. Okay, so let us see an example now. So first example says, determine if the function is continuous at x is equal to 2. Okay, so we need to understand where are we supposed to check the continuity of the function. The continuity of the function we are going to check at x is equal to 2. We are going to check the continuity of the function at this point, correct? But what is the function? That will be given to us. So if you see, this is a piecewise function. It says fx is 3x plus 1 when x is less than 2. The function is equal to 5 at 2, the value of the function I mean, and fx is equal to x square plus 1 when x is greater than 2. I hope this part is clear to all of you. So this is the question, and how to identify where to check the continuity. Even if they don't give you this part, suppose they don't give you x is equal to 2, still you should be able to identify where you are supposed to check the continuity. Obviously, see here, we are supposed to check the continuity at x is equal to 2, correct? So how do we do that? So if you recall all the conditions, they must be satisfied. So we'll first check f of 2, right? Then we will find out limit x tends to 2 minus fx. Then we will find out limit x tends to 2 plus fx. Correct? Let us do that. So firstly, we will find out the value of the function, isn't it? Value of the function, that is f of 2. Fx is already given to us. Fx is 5 when x is equal to 2. Correct? The value of the function fx is 5 when x is equal to 2. So f of 2 is 5, already given. Now, let us talk about the left hand limit, this part. Limit x tends to 2 minus fx. When I say limit x tends to 2 minus fx, it means the value of x is slightly less than 2. So I'll pick up this function, isn't it? 3x plus 1. So I'll write down for less than 2, the left hand limit will be fx is equal to 3x plus 1. You will put x as 2. Limit x tends to 2 minus does not mean minus 2. It means 2 only. So put 2 there, 3 to the 6, 6 plus 1 is 7. Now since you get 7, let us move on to limit x tends to 2 plus, the right hand limit. So for that you will select this, isn't it? So that will be limit x tends to 2 plus fx will be equal to limit x tends to 2 plus x square plus 1. Now instead of x you will put 2. So 2 square plus 1, 2 square is 4, 4 plus 1 is 5. Now understand, the left hand limit is 7, the right hand limit is 5. Is the left hand limit equal to the right hand limit? Observe, it is not equal. Since the left hand limit and the right hand limit, both of them are not equal, what can we say? We can say that the function is not continuous at x is equal to 2. That means at x is equal to 2, there is some break in the graph. Correct? We don't have to draw the graph. It is just for our understanding. Now let us talk about the continuity at a point. Example 2. Determine if the function is continuous at x is equal to 0 for the function fx is equal to sin x by x. So the function fx is equal to sin x by x is already given to us. We are supposed to check if the function is continuous at x is equal to 0 or not. So let us move on to the solution. Now we know that for continuity, limit x tends to a fx is nothing but f of a, isn't it? So we'll find out the value of the function first. F of 0 is already given as 1. So directly we can say that the value of the function f of 0 is 1. So limit x tends to a fx is equal to limit x tends to 0 sin x by x. Limit x tends to 0 sin x by x is nothing but 1. So can I say this is also 1, this is also 1. So we can say that limit x tends to 0 fx is equal to f of 0, which is nothing but 1. Clear? I hope this part is clear to all of you. Simple. So what can we say? We can say that definitely the function is continuous at x is equal to 0. Okay, let's continue. Example 3. Check whether the function fx is equal to 1 by x minus 1 is continuous at x is equal to 1. Now here we are supposed to check whether the function is continuous at x is equal to 1 or not, and the function is already given fx is equal to 1 by x minus 1. So here, as you know, this is a rational function and you can do this orally as well. What will happen if I put the value of x as 1? The denominator is going to be 0, and you know what happens when the denominator is 0. Whenever the denominator is 0, the function is discontinuous, isn't it? Okay, but we'll do it in a systematic manner. So we know that for checking the continuity, limit x tends to a fx should be equal to f of a. So here, the value of the function, that is f of a, is what? F of 1, which is 1 minus 1 in the denominator, and that gives you infinity. So can I say this function itself is undefined at x is equal to 1? So one of the conditions that limit x tends to a fx should exist. So is the value existing here? The value is not existing. We can say that the function is not defined at x is equal to 1. And since the function is not defined, f of 1 does not exist. And when f of 1 does not exist, we can say that the function is discontinuous at x is equal to 1. So this function clearly is discontinuous. Okay, let's have a look at a new example now. Determine if the function is continuous at x is equal to 2. We are supposed to check the continuity of the function, that is x is equal to 2, where the function fx is given as x square when x is less than equal to 2, and 4x minus 4 when x is greater than 2. Okay, so in this case, always remember, if you see such type of conditions, greater than equal to, less than equal to, greater than, less than. That means we need to find out all the three values. Left hand limit, right hand limit, the value of the function at that particular point, all three of them. Okay, let us see how to do that. So first of all, let us focus only on finding the value of the function. Then we'll find out the left hand limit, and then we will find out the right hand limit. Correct? So value of the function, that is f of 2. So what will be f of 2? Now see, this is less than equal to 2. That means equal to 2 is also there. So the value of the function at 2, the function itself will be x square. So can I say f of 2 will be 2 square, which is 4. Clear? Okay. Now let us talk about the left hand limit. Left hand limit also will be this only, no? The function is going to be x square only, isn't it? So here we go. For x less than 2, again put x as 2 here. Limit extends to 2 minus does not mean minus 2. It's 2 only. 2 square is 4. Okay. Now right hand limit. Right hand limit, for that you'll choose this. Correct? And then once you put the value of x as 2 here, you get 4 2s are 8. 8 minus 4 is 4. So observe, this is 4, this is 4, this is 4. That means clearly we can say that the left hand limit, right hand limit and the value of the function at 2, all three of them are equal, that is 4. All the conditions are satisfied, and therefore we can say that the function is continuous at x is equal to 2. Okay, let's continue. Now observe this, we have a function, it is 3x plus 1 when x is less than 2, 5 when x is equal to 2, and x square plus 1 when x is greater than 2. So whenever you have a piecewise function, always remember, we need to find out the value of the function, we need to find out the left hand limit, we need to find out the right hand limit, all of them. Clear? But whenever you have something like this, when you are supposed to find out the value of the function at a particular point, say f of 0, that means you are just supposed to find out the value of the function at 0, and in that case, just find out limit x tends to a f of x, that's it, and that should be equal to f of a. We'll find out the value of function that is f of a, we will find out limit x tends to fx, limit x tends to a f of x, and both of them should be equal. If both of them are equal, the function is directly continuous. So in this way, you need to identify when to find out the left hand limit, when to find out the right hand limit, when to not find the left hand and right hand limits respectively. Okay, let's continue. Now let us talk about the continuity of standard functions. Some standard functions, like we are going to talk about polynomial functions. Going forward, we are also going to talk about rational functions, trigonometric functions, and so on. Polynomial function, you already know what a polynomial function is. Polynomials, you have already studied that in your lower grades, right? So if I say x square plus 2, 5x minus 7, 2x square plus 8, all of these are polynomials. And whenever we talk about polynomials, we know that the degree is the whole number, right? The power is the whole number there, and those functions are polynomial functions. So this is the general form of polynomial functions. That's not that important. You can have some examples here. So here is a polynomial function. Now see, in polynomial function, if you see, there will be no variable in the denominator, right? In the denominator, there is no variable, because if there is any variable in the denominator with higher degree, it goes up, that becomes negative. So we know that the degree cannot be negative there, it has to be non-negative whole number. So polynomial function is always continuous because there is no break, right? This function is continuous everywhere on the set of real numbers. So if you pick any real number r, right, and if you put the value of x there, you can put anything, 1, 2, 3, any real number, not even natural or whole numbers. You can put square root also. You are going to get some value of fx. That means fx is going to be defined on every value of r. Correct? So remember that polynomial function is always continuous. Now let us talk about rational functions. Rational functions. You already know what are rational numbers. Rational numbers are those numbers which can be represented in the form of p by q, right? So if there is a number which can be written in the form of p by q, that is a rational number. But here we are going to talk about rational functions. So what are rational functions? Rational functions are those functions which can be expressed as the division of two functions basically, that is px by qx. You can see, correct? Px by qx. So where p of x and q of x, what are both of them? Px and qx, both of them are polynomials. So whenever you have px as a polynomial, you have qx as a polynomial, and you divide both of them, or you take the fraction, you can say. So in that case, you can say that it is a rational function, right? So rational function is continuous everywhere except q of x equal to 0. So whenever the denominator becomes 0, the rational function is discontinuous. Let us see an example now. So we have fx is equal to 3x square minus 4 by x square minus 1. So this is a rational function, isn't it? Now, is this rational function always continuous on set of all the real numbers? Actually no, because if you see x, if I put the value of x as 1, 1 square minus 1 will become 0. Even if I put the value of x as minus 1, minus 1 square is 1, 1 minus 1 is 0. So definitely, whenever x is 1 and whenever x is minus 1, this function is going to be discontinuous. So I can say that at x is equal to 1 and x is equal to minus 1, this function is discontinuous. But for all the other points, there is no problem. You put any other number, there is no issue at all. Correct? So only there will be two breaks. One break will be at 1, x is equal to 1. The other break will be at x is equal to minus 1. Clear? Because the denominator becomes 0. Now let us talk about the continuity of standard functions. So here we are going to talk about the continuity of trigonometric functions first. We know that there are 6 trigonometric functions: sine, cos, tan, cot, sec, cosec. Let us talk about sine. You have seen the graph of sine. It is always continuous. So we can say that it is continuous for all x belonging to R. Similarly, if I talk about cos x is also continuous for all x belonging to R. If I talk about tan x, for tan x, it is discontinuous, where at the integral multiples of pi by 2. So wherever we get 90 degrees and multiples of 90 degrees, in that case, tan is going to be discontinuous, right? Then we have cosec, same thing, integral multiple of pi. Then we have sec x, for that, integral multiples of pi by 2. And finally, we have cot x, that is integral multiple of pi. It is discontinuous. So this is the continuity of trigonometric functions. So if you see, only sine and cos are continuous for all x belonging to R. Now let us talk about the continuity of exponential function. Exponential is a raised to x, right? 3 raised to x, 4 raised to x, 7 raised to x, and so on. So continuity of exponential function. The exponential function fx is equal to a raised to x, where a is greater than 0, is continuous for set of all real numbers x. So a raised to x is always continuous. There is no problem at all, provided the value of a is greater than 0. So we have an example 2 raised to x. You put any value of x, there is no problem. You can put negative value, you can put positive value, you can put square root. You will get some value of fx. Fx will exist. That means exponential functions are always continuous. Clear? Okay. So it is continuous on everywhere, that is on the set of real numbers. Let's continue. Now let us talk about the continuity of logarithmic functions. So you already know that fx is equal to log x to the base a. Suppose that is your function, where a is greater than 0, of course, and a is not equal to 1, because we know that log of 1 is 0, and that comes in the denominator, it will become not defined. Is continuous for all x greater than 0, right? So if the function is natural log of x, it is continuous, right? This function is continuous for x greater than 0. I hope this part is clear, correct? So logarithmic functions are undefined for this, you already know, isn't it? That x is less than equal to 0. In that case, logarithmic functions are undefined and they're continuous only for positive x only. That is, the value of x has to be greater than 0 only. Clear? Okay. Let us talk about some examples now. Check the continuity of the function. So it's a simple question, basic question based on continuity. We are supposed to check the continuity of the function fx is equal to x square minus 1 by x minus 1. and we are supposed to check the continuity of this function at x is equal to 1. Let us move on to the solution. So fx is equal to x square minus 1 by x minus 1. Correct? So is the function continuous? You already know the answer to this. What will happen if x is 1? If I put the value of x as 1, this will become 1 minus 1, that is 0. And once I get the denominator as 0, right, we can say that this function is discontinuous or undefined, right? We can rewrite this to remove the discontinuity. You can rewrite this as x minus 1 into x plus 1 by x minus 1. This gets cancelled because x square minus 1 is like your a square minus b square. And then you get x plus 1 where x is not equal to 1, right? X should not be equal to 1, of course, because in that case the denominator becomes 0. Okay. Function is not discontinuous. So no need to give the entire briefing. We already know that this function is discontinuous because denominator becomes 0. That's it. Okay. Let us see an example. It says, check the continuity of the function fx is equal to tan x at x is equal to pi by 2. Now the value of x is pi by 2. So you need to know the trigonometric table that we have studied in our grade 10 as well. And I'm very sure you know that. Pi by 2 is 90 degrees, tan 90. Tan 90 is sin 90 by cos 90. Sin 90 is 1, cos 90 is 0. 1 by 0 is not defined, right? Okay. So here can I say the function tan x is known to be undefined here. Integral multiples of pi by 2. So definitely, even if I have 1 pi by 2 there, that is pi by 2. So this function will have a jump, right? That is, there is going to be a break at 90 degrees. So clearly, if you look at the graph, we can say that at integral multiples of pi by 2, this keeps on breaking. So the function is discontinuous, right? Simple question. Let us see one more question. Prove that fx is equal to e raised to x is continuous for all x belonging to R. Okay. Now for all x belonging to the set of real numbers e raised to x. Firstly, can I say that e raised to x is nothing but your exponential function, but that looks in the form of a raised to x. But what was the condition for a? The condition for a was a should be greater than 0. But here we don't have a, here we have e. What is the value of e? If you remember, the value of e is approximately 2.7, right? If I take up to 1 decimal, of course. So e is 2.7. Can I say 2.7 is greater than 0? So this is definitely greater than 0, right? So the condition is satisfied. Your a is greater than 0. And we already know that the exponential functions are always continuous. So in this case also, we are going to say that the function is continuous for all x belonging to R. Clear? And the graph of e raised to x looks like this. Okay. Now let us talk about removable discontinuity. So there are some discontinuities that can be removed. Not all the discontinuities can be removed, but in general some discontinuities can be removed. So function has a removable discontinuity. When does the function have a removable discontinuity? Although you are not going to have questions based on this, let us try to understand the concept. A function has a removable discontinuity at x is equal to a. Firstly, the limit extends to a. Instead of 1, this should be a. Limit extends to a fx should exist. That means it should not be not defined. You should have some value for limit extending to a fx. But f of a is either undefined or not equal to the limit. Let us try to understand that. Here is the left hand limit and the right hand limits. Now understand this very carefully. If the left hand limit and the right hand limit do not exist or they are not equal, then you cannot remove the discontinuity. That means if the graph looks something like this, left hand limit is like this, right hand limit is like this, you cannot remove the discontinuity of this. But then when can you remove? You can remove the discontinuity at a particular point. So if the graph is like this and the continued graph is like this and there is only one break here, in such cases you can remove the discontinuity. So this point can be filled. This point can be filled provided you need to have some value here for that particular x. In that case only we can fill this gap. Okay, let us see an example. Removable discontinuity. So here you have, basically we know that removable discontinuity, sorry, not removable continuity. Fx is equal to x square minus 4 by x minus 2, and the value of fx is 4 if x is equal to 2. So basically this graph is breaking at x is equal to 2, but there is no problem. This discontinuity can be removed. How? Because what they're doing is they're saying x is not equal to 2. Then this is the function. Definitely at 2 it is breaking, isn't it? Because if I put 2 here, so what they're doing is at 2, they're filling the gap by giving the value of fx as 4. So there was a gap there at 2. At x is equal to 2, gap in the graph. That gap, that point is filled by what? 4. That's how it is. So if you see, if the function is continuous at x is equal to 2, obviously the function is not continuous, because if I find f of 2, I'll put 2 here, correct? Solve this further. You can see there, this part. Correct? F of 2 is what? Not defined. So the function is discontinuous. See here. So the function is discontinuous at x is equal to 2. Correct? But this is a removable discontinuity, because at 2 you have the value as 4. If they don't give you this, and if this is the case, then definitely this particular function is discontinuous at x is equal to 2. To fill that gap at x is equal to 2, the value of the function is 4. Okay. Now non-removable discontinuity, as I told you, if there is a break, complete break in these two, then it is non-removable. That is the left hand limit and the right hand limit. If both of them are not equal, it is a non-removable discontinuity. Let us see how. So the left hand limit, this is your left hand limit, correct? You put the value of x as 1. Here you will put 1. So 1 plus 2 is 3. When you talk about the right hand limit, here it is. You put the value of x as 1. That becomes 3 minus 1. That gives you 2. Now this is 3. This is 2. The right hand limit and the left hand limit, both of them are not equal. Since both of them are not equal, we can clearly say that the function is discontinuous, obviously, and it has a non-removable discontinuity. It has a non-removable discontinuity. I hope this part is clear to all of you. Now let us talk about the continuity in a particular interval. So here we have a closed interval a to b. So here we are not talking about continuity on set of all the real numbers. We'll have a small interval, that's it. So fx is continuous on the closed interval a to b when it is continuous at every point in the open interval, first of all. So to be continuous in the closed interval, firstly it needs to be closed and continuous in the open interval. It should be continuous in the open interval, not closed. Not only that, also we need to have this condition that fx is continuous on a to b closed interval if it is continuous on every point in the open interval, and limit x tends to a minus fx should be f of a, that is continuity from the left and continuity from the right should be satisfied. That is limit x tends to b plus fx should be f of b, and limit x tends to a minus fx should be f of a. If all these conditions are satisfied, we can say that it is continuous in the closed interval. So basically what we are doing is, firstly we will find out the continuity in the open interval. In the open interval we'll find, then we'll find at a, then we'll find at b, and a, b and the open interval in the middle. That's it. If all the conditions are satisfied, it is continuous, otherwise it is not. Even if you get a break at one point at a or b, then also it is not continuous. Clear? Okay. So let us see an example. Fx is equal to sin x. Check whether fx is continuous in the interval 0 to pi. Now this answer we already know. We already know that sine function is continuous, right? This is how sine looks like. So it does not matter what interval you are going to take. And between 0 to pi, correct, you have all the values here, right? So there is no break here. So since there is no break, clearly we can say that fx is equal to sin x is a continuous function, correct? Sin x and cos x are the only trigonometric functions which are continuous for all x belonging to R. Okay. Now let us see an example. Discuss the continuity fx is equal to under root 16 minus x square on the closed interval minus 4 to 4. On the closed interval minus 4 to 4. Now look at this function. There is no denominator here. Correct? Firstly, we'll check the continuity in the open interval minus 4 to 4, isn't it? So the domain is minus 4 to 4. So x is any point in this domain. X is any point. It can be minus 3, minus 2, minus 1, 0, 1, 2, 3. It can be 1.5, 2.5, minus 1.5, anything. Doesn't matter because x is any real number in the open interval, right? So this a belongs to the open interval, minus 4 to 4. So if I check the continuity and find out the value of the function at a, that is limit x tends to a, can I say instead of x I can put a, that becomes 16 minus a square. Now if I say a as 4, what will be f of 4? F of 4 is going to be 0 because this is 4 square 16, 16 minus 16 is 0. What will be f of minus 4? F of minus 4 is also going to be 0. So f of 4, f of minus 4, both of them are same. Limit x tends to 4 minus fx, that will also be 0. Limit x tends to 4 plus fx, that is also going to be 0. So can I say that the function fx is continuous at every point on the open interval minus 4 to 4, and also it is continuous at the right as well as on the left, at the right of minus 4 and on the left of 4. So clearly we can say that this function is continuous in the closed interval. Correct? The function is continuous on the closed interval minus 4 to 4. Simple question. Let's continue further. Now let us talk about the algebra of continuous functions. When I say about algebra of continuous functions, here I am going to talk about the arithmetic operations basically, that is addition, subtraction, multiplication and division. So two functions. Definitely we need two functions because we are doing some algebra, we are doing some arithmetic, we are doing some calculations. So if fx and gx are continuous at C, fx and gx both of them are continuous at C, then their algebraic combinations are also continuous at C. Let us see how. That means fx is continuous, gx is continuous, then their addition fx plus gx is also continuous at C. That means there is no break if you add the two functions. Same goes with subtraction. Fx is continuous, gx is continuous. If you subtract the two functions, they are continuous at C. Same is with multiplication. Fx into gx is continuous at C. Fx by gx is continuous at C, but provided you know the condition, because this becomes a rational function now, right? Since this becomes a rational function, this g of x, after putting the value of x as C, should not be 0, correct? If g of c is not 0, there is no problem, this is continuous. So only for division, this condition needs to be checked very carefully. Let us see some problems based on this as well. Two functions are given. Fx is equal to x square, gx is equal to sin x. We are supposed to show that their algebraic combinations fx plus gx and fx minus gx, both of them are continuous. Now see, firstly always try to identify what type of function do you have. Fx is x square, right? Can I say it is a polynomial function? Yes. What can you say about polynomial functions? We know that all the polynomial functions are continuous, so there is no problem at all. So x square is always continuous on any real number r. Gx is equal to sin x. You put any value of x, any real number, we know that the graph of sine does not break. So sin x is also continuous. X square is also continuous. If x square is continuous, sin x is continuous. That addition is also going to be continuous. So how are we going to write it down? We'll write it like this. First thing, we'll compute the value, that is f of 0 plus g of 0. That is going to give you sin 0 is 0, 0 square is 0, so 0. Then left hand limit and the right hand limits. So limit x tends to 0 plus addition of these two, we'll put 0 only. You're going to get 0. 0 minus, again you'll put 0. You're going to get 0. This is 0. This is 0. Value of the function is 0. So yes, we can say that fx plus gx is continuous. Same goes for subtraction. This is not going to change, right? So fx minus gx, same thing. We'll find out f of 0, that is 0 square minus sine 0, same thing. 0 minus 0 is 0. Correct? Then left hand limits, right hand limits. This is your right hand limit, answer is 0. This is your left hand limit, answer is 0. All three values are same. So it is continuous. Simple. There is nothing much in this. That's it. Okay. Let us see one more example. Now, again algebra of continuous functions. There is multiplication between fx and gx. So fx is x square, gx is e raised to x. Again, you don't need to do anything much. You can do this orally because x square is a polynomial function. E raised to x is an exponential function. We know that e raised to x is always continuous at any value of x as real number. So their multiplication is also going to be continuous. So same logic we are going to apply. Firstly, we will find out the value of the function at 1, that is f of 1. So f of 1, x square into e raised to x, correct? That is f of 1 into g of 1, sorry. So 1 square into e raised to 1. 1 square into e raised to 1 is e. E raised to 1 is e only. Now left hand limit, right hand limit. Same thing. Nothing is going to change. This is e. This is e. Again, this is 1. This is 1 minus. 1 minus does not mean minus 1. So again, same thing. This is e. That's it. 1, 2, 3. Condition is satisfied. They are continuous. Simple. Very simple questions. Okay. Now rational function. We are supposed to check the continuity of this function and we are supposed to check whether f of x by g of x is continuous at x is equal to 2. Okay. Same thing we are going to do. We'll do f of x by g of x and find out the value at 2. So f of 2 by g of 2. F of x itself is 2. G of x is x square, that is 2 square. So 2 by 2 square, 1 by 2, correct? Now left hand and right hand limits. So left hand limit, see x by x square, no? X by x square, 1x will get cancelled, x is 2, so 1 by 2. This is also 1 by 2 by the way, correct? And x tends to 2 minus is also 1 by 2. All the three values are the same. Nothing is changing here. So definitely we can say that f of x by g of x is continuous at x is equal to 2. I hope this part is clear to all of you. Very simple. Put the values, get the answer. That's it. Okay. We have one more. Now find the relationship between a and b so that the function f defined by, okay. Now we are supposed to find out the relation between a and b. Now what is the meaning of finding the relation between a and b? A can be double of b, b can be half of a, b can be 10 times a can be 5 times b, a can be 4 more than b. That's how we need to create a relation. So whenever they say create a relation, indirectly create an equation. Indirectly create an equation between a and b at the end. You don't have to find out the value of a and b. I hope this part is clear. Okay. Now, here it is already given that the function is continuous. Understand the question. The function is already continuous. So can I say the left hand limit and the right hand limit, both of them are already equal given? They're already equal, correct? So, f is a continuous function at x is equal to 3, then limit x tends to 3 minus fx and limit x tends to 3 plus fx, and of course f of 3, all the three values are equal. So let us equate that. This is limit x tends to 3 minus fx, correct? So that becomes, instead of x you put 3, that becomes 3a plus 1. Then if I talk about limit x tends to 3 plus fx, that becomes 3b plus 3. So this is 3a plus 1, this is 3b plus 3, correct? So can I say we can find out f of 3, same thing, doesn't matter. Now equate these two, ignore this, just equate these two. So 3b plus 3 is equal to 3a plus 1, same thing. Transpose the terms, a will be equal to 3b plus 2 by 3, and then finally a is equal to b plus 2 by 3. So this equation is nothing but the relation. That's it. So this is the relationship between a and b. I hope this part is clear to all of you. Simple? Okay, let's continue. Find the value of k. Such type of questions can be asked in the exam. find the value of k where the function is continuous at x is equal to 5. So the function is already continuous. So can I say the left hand limit and the right hand limits are equal? Of course, yes. Function is given. Function is continuous at x is equal to 5. Then the left hand limit, right hand limit, and the value of the function will be same. Even if we ignore this, doesn't matter because we need equality between two terms. That's it. Left hand limit is what? 3x minus 8. Right hand limit is what? 2k. So 3x minus 8 will be equal to 2k. Correct? This you have solved it separately. 3x minus 8. But x is 5. 5 minus means 5 only. Correct? Not minus 5. 3 5 is 15. 15 minus 8 is 7. And this is extends to 5 2k. Don't put 5 instead of k. X is tending to 5. K we don't know. So 2k and 7. You will equate that. Equate 2k and 7. That's it. K is equal to 7 by 2, 3.5. That is the value of k. So I hope you enjoyed the session on continuity and you learned a lot in this. Such type of problems can be asked in the exam. So this was our one-shot video on continuity. But this chapter also comprises of differentiability, and that we are going to see in the next session. So stay tuned and see you in the next session on differentiability. Bye-bye.